So today we will talk about electromagnetic induction. So if you have your book with you, then you can turn to page 262. For last semester, we have talked about how to use the electricity to generate the magnetic field or the magnetic force, like F equals to VIL to QVB. Okay, so if you have the electricity and you put it into the magnetic field and you have the magnetic force, or so if you have a solenoid and there is a battery to give it to provide the current, then there is the magnetic field around it, which the equation is mu C B equals to mu 0 I over 2 pi r. Okay, so for what we learned last semester is all about from the electricity to some magnetic properties. So in this semester, then we learned how to create the electricity or the electric field by using the magnetic field. Okay, so one of the most common example is the power station. Okay, so we use the magnetic field to generate electricity in the power station, but I found that I have nothing to demonstrate this effect, so I will tell you very directly. Okay, so before we learned electromagnetic induction, that we need to know what is Lenz law. Okay, so in Chinese, which is 冷气定律. Okay, so the Lenz law says that an induced current it presents it always flows in a direction so as to oppose the change that produces it. Okay, so I think you can't understand this statement, right? So there is another way easier to learn this law. Okay, so we can actually you can call this law as the 渣男. Okay, so what is 渣男? Okay, so if you come close to the 渣男, then the 渣男 will reject you. Okay, if you moving away from the 渣男, then the 渣男 will try to attract you. 簡單啲嚟講咧，咩叫凌次定律咧？就好似一個渣男咁樣啦。OK， 如果你行緊一個渣男咧，咁佢就唉唔好唔好唔好。如果你要走咧，咁佢就會掹住你啦。好啦，咁點樣用咧？我哋嚟睇下呢度。So if there is a magnet moving toward a solenoid, so what's the difference between these two solenoids? So for this one, there is the power source, so it can generate the electricity. The directions of the electricity is pointing downward. Okay, so and then to use the right-hand grid rule, then you can find the directions of the magnetic field. For this case, there is no battery. Okay, so we replace the power source with the emitter, and then we have a magnet. Okay, so the magnet is moving toward this solenoid. So think about what will happen if the magnet is moving toward the solenoid. So first, you can draw the magnetic field around this magnet. Okay, so the magnetic field is starting from the North Pole toward the South Pole. Okay, so don't forget that the magnetic field lines can't cross each others. So if the magnets come closer, then more and more field lines will pass through this solenoid. Okay, so more and more field lines point toward the right hand side. Okay, so now let's apply the 渣男定律。越嚟越多 field lines point toward the right hand side. So the solenoid will create the magnetic fields against this trend. Okay, so to oppose the change that produces it. So in this case, more field lines pass to the right hand side. So this solenoid will create the magnetic field point to the left hand side. Okay, so we try to resist it. And now how can we find directions of this induced current? Why do we call this induced current? Because originally there is no current at the beginning. I forgot if I turn on the record motion or not. Yeah, perfect. Okay, so we can use the right hand grid rule because the magnetic field is pointing toward the left hand side, right? So the current create this magnetic field is rotating in anti-clockwise. Okay, so if we feel from this position, so here is the directions of the induced current. So originally there is no current. However, if you move the magnet toward the solenoid, so in order to resist it, it will create a current. Okay, so how to determine the directions of current? So first, this solenoid will try to resist the motion. Okay, so because more field lines point to the right hand side, then this solenoid will create the field lines point to the left hand side. Okay, so and then you use the right hand grid rule, then you can find the directions of this induced current. So in this case, which tells you that if there is change in magnetic field passing through a loop or a solenoid or a closed circuit, wherever there is change in magnetic field in a loop, then that will be induced voltage or current. So this is the principle behind the power station. Okay, so the power stations rotate the generator. The generator is actually the motor. When it generates electricity, then we call this generator. And actually, its structures and everything is same to the motor. So if you rotate the motor, rotate the generator, then there is changing in magnetic field. So if you have a closed loop, then you can generate electricity. Similar to this case, if there is change in magnetic field in a closed loop, then there is induced current or voltage. Okay, so this is the first one, first part of the 渣男定律 ，right？ 你嘗試去靠近佢嘅時候咧，咁佢唔俾你靠近佢，點解啊 ？The magnetic field created is pointing to the left hand side. So actually, this is the north pole, this is the south pole. So this 渣男 is trying to reject you if you are coming close. Okay, so now let's see what will happen if we change the directions of this magnet. Okay, so now you will annoyed and try to lift this guide, so moving toward the left hand side. Okay, so I'm going to erase this one, and actually you need to copy this diagram on your notebook, and I will check when you come back to school. I don't know when you will come back to school. So you have a complete circuit, and magnet is now moving toward the left hand side. Then. So now let's field lines point toward the right hand side, right? So let's field lines pointing toward the right hand side. So if you move the magnet to far positions away from this solenoid, then the magnetic field will be 0. So in this case, when you move this magnet toward the left hand side, and the magnetic field strength, the field lines pass through this solenoid will be decreased, right? 好啦，而家問題啦，畫錯咗方向。跟住呢邊。Sorry. Okay, so the magnetic field from the north pole is pointing toward the right hand side. So if you move it leftward, then the magnetic field strength will be decreased. Okay, so what will 渣男 do? If you lift him, then he will try to attract you. Okay, so because less field lines point to the right hand side, then this solenoid will create a field line point toward the right hand side. Okay? We'll create a magnetic field point direct the right hand side. Now you can apply the right hand grip rule. Then you can find the directions of the induced current and see what will happen. So this is the north pole, right? Because the magnetic field is coming out from this end. So in the other way, this one is the south pole. And actually they will attract each other. So when the magnet is leaving, then the solenoid will try to attract it. 即係當你離開佢嘅時候咧，咁咧佢就會嘗試去追翻你。但係你追佢嘅時候咧，咁佢就唔理你啦。Okay, so let's reverse the polarities of the magnet and see what will happen. So now, the south pole of the magnet is closer to the solenoid. Okay, so and think about what will happen. So first, so let's draw the directions of the magnet. The magnetic field point from the north to the south. Okay, so if this magnet is coming closer to this solenoid, then more and more field lines pass through this solenoid point to the left hand side, right? So because if the south pole is closer, then more field lines pass through this loop will point to the south pole. Okay? So in this case, more field lines point to the left hand side. Okay? Then what will the solenoid do? It will try to resist this trend. Okay, so try to resist the trend that more and more field lines pointing to the left hand side. So in this case, the solenoid will create a magnetic field lines point to the right hand side. So again, when this magnet comes closer to the solenoid, more field lines point to the left. So the solenoid will create the field lines point to the right. And then use the right hand rules here, give you the directions of the current. Okay? So the last case, so you can do it on your own. So if you have a magnet which is the south pole closer to the solenoid. Okay? Oh yeah. Then you can see what will happen or what is the direction of the induced current. And the induced magnetic fields, of course, the directions are reversed from the previous case. So this is the simplest applications of the Lenz law. 咁咧，淨係記住一樣嘢就得啦。越嚟越多向右嘅，咁我就整啲向左 ，OK？ 譬如越嚟越少向右嘅，咁我就整啲向右。總之永遠都同你倒翻轉咧，咁呢個就叫 Lenz law，OK？ So now we have another example, or rather another applications for applying the Lenz law. So let's erase this solenoid first. Okay, so for examples, we have a magnetic field. We have a magnetic field pointing inward. We have a magnetic field pointing inward. And we have a loop which is moving toward the right hand side. Okay, so moving into this magnetic field. Okay, so now we will find the directions of the induced current. So be careful that originally there is no current. Okay, so there is no current, only a plain loop moving toward the magnetic field. And see what is the directions of the current, induced current. So when this loop moving into the magnetic field, then more and more cross enclosed in this loop, right? So originally there is no magnetic field in this loop. So when it's coming into the magnetic field, then more and more cross enclosed in the loop. Okay, say in the loop. More and more cross or field lines enclosed in the loop. Okay, so don't forget that this is a tunnel. Everything is a tunnel. Okay. Yes. So more and more cross enclosed in the loop. So the loop will induce some magnetic field lines which is pointing outward. Okay. I use the green color to represent the induced magnetic field and the induced current. So the loop creates some magnetic field pointing outward in order to decrease the effect of the inward magnetic field. So use the right-hand grid rules to find the directions of the induced current. To find the directions of the induced current, then you will find that the directions of the induced current is actually moving in anti-clockwise. Okay? So that's how to find the directions of the induced current. So think about the directions of the induced magnetic field first. Okay, so if it's coming out, then use the right-hand grid rule, then you will find the directions of the induced current. So for the second position, so when it is leaving the magnetic field, then less cross and close. Okay? So less cross and close in this magnetic field, then the loop will induce some cross. Okay, so induce cross in the loop. So induce some cross because less and less cross enclosed in the loop. Okay, so here are the directions of the induced current. So you can see that the directions of the induced current are opposite for these two situations, because for the first one, more and more cross enclosed. For the last one, less and less cross enclosed. So if the loop is moving inside the magnetic field, will there be any induced magnetic field and induced current? Okay, so the answer is no. The answer is no. No induced magnetic field and current. Why? Because in this case, the whole loop is now submerged inside the magnetic field, right? So if it is moving, you can imagine that if you are totally submerged into the water, then the water and cold doesn't change, okay? Because the visualized will be the visualized field, all the areas enclosed by the loop. So when it's moving inside the magnetic field, then the numbers of field lines enclosed doesn't change, okay? Or the magnetic field enclosed to 0. There is no change in magnetic field, okay? So that there is no induced magnetic field and induced current. Okay, so if you want to create some electricity, then there must be change in magnetic fields or change the numbers of field lines enclosed in the loop. Okay, so this is another example of the Lenz law. So now we have the third example of the Lenz law. Okay, so again, let's draw the magnetic field first. Okay, so if you have a single rock, moving inside the magnetic field, so will there be any induced current or induced voltage? So in this case, there is no loop, right? So it seems that you can't apply the Lenz law. However, you can imagine this situation is like this. When the rod moves to this position, then the enclosed field lines will be this flow process. Okay? So originally there is no enclosed field lines, and after it moves to this position, then it forms a frame and enclosed whole field lines. So you can do the same things because there are more and more cross, right? So there are more and more cross enclosed. So it's induced some dot. Okay? So induce some dot or the magnetic field pointing outward. So if there is some magnetic field pointing outward, okay, then what is the directions of the current? Okay, so the directions of the current so it's pointing into this direction. Okay, but in this case, there is only one rod, right? So there is the same rod, but not a real loop. So here is the directions of the induced current. Okay, so but not downward. But it's quite complicated or quite difficult to memorize this method. Okay, because you may think, it's a loop. Okay, then the current is pointing downward. Then you will make it wrong. Okay, so in order to solve this problem, and I will teach you another method. Okay, so this method is actually same to the FBI rules or what we call the Feynman's left-hand rules. So now we do the same posture by our right hand. We do the same posture by using the right hand. So for the left hand, which is FBI, force magnetic field current. For the right hand, it is VBI. Velocity of the rod inside the magnetic field. Velocity of the rod inside the magnetic field. Directions of magnetic field. Okay, so and then induced current. Because there is no current at the beginning, so this I is the induced current. So let's fit this posture in this situation. Okay, so the magnetic field is pointing inward. The magnetic field is pointing inward. The velocity is pointing toward the right hand side, and then your current finger is not pointing upward. So the induced current is pointing up, or the induced voltage is pointing up. Okay, so that's how you can find the induced voltage for a single rod. Use the right field-linked right-hand rules. Okay. So now, when it's moving, then you can treat this thing as the power source. So actually, it becomes like a battery. So I would like to ask you a question. So which end is the positive terminal of this temporary battery? So you can memorize these situations like this. If you connect a wire with these two ends, then the current will flow out from the upper end, right? Current flows out from the upper end so that the upper end is positive terminal. And then the lower end is negative terminal. Okay, so this is the method for you to find the induced voltage of a single rod. Okay, so use the right-hand rules. And actually, you can use the filament right-hand rule to solve the previous case. Okay, so let's see what's the meanings of applying the filament right-hand rules for the previous case. Okay, so do you remember that you have a loop moving into the magnetic field, and you have a loop, the same loop is moving out from the magnetic field. So now this rod is submerged into the magnetic field, right? But not this one. So only this end can be applicable by the magnetic, by the filament right-hand rules. Okay, so apply the filament right-hand rules, and you can find the induced current is falling up. Okay, so which is same to the situations you used the Lenz law to explain this. Okay, so for you to use the Lenz law, you need to create some dots. Use the right-hand grid rule and directions of currents is pointing in the anti-clockwise. By applying the filament right-hand rules, VBI, okay, so velocity of this rod is moving to the right-hand side, magnetic field inward, current upward. So you get the same result. So for this one, okay, so for this one, the loop is now moving out, right? So this end is inside the magnetic field, but not this one. So let's see this one. So VBI, the current is falling upward. Okay. So if we complete it, then it is in clockwise. So actually, you can solve both situations by using the Lenz law or the right-hand rules. Okay, so it depends which method is more familiar with you. But if you want to use the filament right-hand rule to solve this kind of question, then it's very difficult to explain. Then I would suggest you to use the Lenz law whenever you see this kind of motions or questions. OK？ 好啦，講得簡單啲咧，我通常係點樣分咧？如果一條 single rod 咧，咁我就用 filament right-hand rules。其他全部情況，凡係有 loop 嘅嘢，我都用 Lenz law。OK， 一條就用 right-hand rules， 其他我都用 Lenz law 去用就得㗎啦。OK， 好似講完呢個，唔係呢個，呢兩個。係，咁咧大家就記得做功課。功課就喺我會 send 俾你，係一份 Google Form。拜拜。